So this marks the start of chapter 5, which is going to be introduction to differentiation. I'm so sorry. All right, so we're going to be starting with differentiation, and differentiation is a part of calculus. So there are two main branches. You do differentiation, you do integration. So differentiation and integration, when we talk about calculus, we're mostly going to be studying about change. That is the central idea. Something is changing, and we're trying to figure out how things change and so on. So let's start with something that we're familiar with. Let's start with our straight line graph. All right. So I give you this straight line graph, and I give you the equation mx plus c. And I ask you, what is the slope of this line? Well, you will tell me, hey, the slope is just m, right? This is the slope. Or another way to say slope is to say the gradient. I have my y-axis here, I have my x-axis here. Now geometrically, let's think about what does the slope or the gradient represent. Well, the slope or the gradient is the change in y per unit change in x. Or another way to phrase it is to say the rate of change of y with respect to x, right? Rate of change of y with respect to x, or it's the change in y per unit change in x. So if I give you y is equal to 2x plus 3, your slope is 2. What does this mean? Well, your slope is just 2 over 1. That is the change in y. So that means, so when we read it as 2 over 1, this means that, hey, if my x variable, so 2 basically means if my x variable changes by plus 1, so if my x variable increases by 1, my y variable changes by plus 2, right? So that is what the slope means. If my x increases by 1, then my y variable increases by 2. Another way to think about, if I had minus 2x, then if my x variable changes by plus 1, my y variable changes by minus 2. So x is always we're gonna consider it increases by 1. All right. So now let's look at a more practical example. Is that if I had, say, time on my x-axis, and if I had something familiar, let's say displacement on my y-axis, then the slope of this displacement time graph is going to be my velocity, right? It's the rate of change of displacement. That is velocity. Is the rate of change of displacement. So the slope is going to be, is the slope of a displacement time graph, right? So basically, we have a graph. A graph plots two variables, one on the y-axis, which is our dependent variable. We have our independent variable on the x-axis. And when we take the slope, we are studying how your y variable changes per unit change in your x variable, how your dependent variable changes per unit change in your independent variable. So now we know, sort of, we have an intuitive idea, right? So if I say that my velocity, if the slope of this line is 2, what does it mean? Well, that means that if my time increases by 1 second, my displacement increases by 2 meters. So therefore, 2 meters by 1 second, you get your velocity to be 2 meters per second, right? So that is the idea. However, we always don't have a linear graph to work with, right? So sometimes our displacement time graph, or basically any graph that we're looking at, may not be linear. So it could be something like, say, this graph in green, right? So now let's look at the slope. Let's try to think of a pattern for the slope. Let's look at the slope at this point, right? So the slope is going to be represented by the tangent line at this point, right? So if we just look at how this curve is changing here, as represented by the purple line, now let's take another point, right? See? So now, as we investigate these 3 points, right, you look at these 3 straight purple lines, and you will notice intuitively, you can see that these have different slopes, right? These purple lines have different slopes. So therefore, the gradient of the green curve is not same, it's not constant. It changes. That is the main idea. The gradient of the green curve is not constant. So how do we find, the question is, how do we find the gradient or the slope at any given point? So that is the main question. And the answer is derivatives. A derivative can give you the gradient at a specific point. All right. So now, let me erase everything and I'll draw stuff again. All right. What? Okay. Anyways. All right. So now we have this green line here, something like this. Okay. So now we want to find the slope at a particular point, right? You want to find this gradient at a particular point, but we don't know. So let's use something that we do know to solve this problem. So let's say I want to find the gradient at this point. And let's sort of write this as a function. F of x, y is equal to f of x, right? And this is x, all right. So this is going to be x, and this point on my y-axis is going to be f of x, right? X is my input, my output is f of x. So this coordinate is going to be x comma f of x. So let me write it actually here, x comma f of x. All right. We want to find the gradient here, but because we don't know, right? We don't know what the gradient at this point is. So let me plot another point. So let me go h units away from x. So this is going to be x plus h. So I'm just going moving h units forward from x. And on my y-axis, I have f of x plus h. All right, so this point is going to be x plus h, comma f of x plus h. All right, so now let's draw a straight line connecting these 2 points. That is the red line, right? The red line connects these 2 points. Now, can I find the slope of the red line? I can. This I can. So M, and we will call this the secant line. The secant line connects these 2 points, right? So it crosses this graph twice. That's why we're going to call it the secant line. All right, so we know the slope. We can find out the slope of the secant line, right? So the secant line is basically this red line because it crosses the green graph twice at 2 different points, right? If I extend the line, it's going to look something like this. So I can find the slope of the secant line. And that is going to be y2 minus y1 over x2 minus x1 minus x. So that is just going to be h, right? But the secant line is so if you look at this, right? Our target, we want to find the slope at point x. The slope at point x is going to be the slope of this purple line. So this is tangent line. The tangent line will cross this curve at only 1 point, right? So the tangent line is the good approximation is the value of the slope at x. The secant line is a bad approximation, right? You can see that the slope of the red line is going to be very different from the slope of the purple line. That is the target line, right? So now, let's imagine that we make h smaller. right? If I take a smaller value of h here, and I fixed x, so I take a smaller value of h, and now the slope of my tangent line is this, my secant line is this black line. It's getting closer to the slope of my tangent line. I take still a smaller value of h, and you will notice that the slope of this light green line, lime line, is very, very close to the slope of the tangent line. So the idea is, if I take smaller and smaller values of h, then the slope of secant line is approximately the slope of tangent line, right? And if h is 0, then it's exactly the slope of the tangent line. So therefore, we call this the limit. And basically, it's not included, but the idea is that if your h is closer and closer and closer to 0, the h here, if it gets closer and closer to 0, then m secant is going to be the slope of your tangent line, right? The slope of your secant line is going to be the slope of your tangent line. So limit as h tends to 0 of f of x plus h minus f of x over h, that is going to give you the slope of the tangent line. And this expression here is known as the derivative. The derivative of the graph f of x at point x. So this is the expression, not at point x, but basically this is the expression for the derivative of f of x. So we will write this as sometimes as dy by dx, right? So now you know that dy by dx is simply the slope of the tangent line at a particular x. Slope of the tangent line at a particular x value is just dy by dx. And another way to represent it is f dash of x. That is what we call the first derivative. So now you have an intuitive idea of what the derivative is. All right. So now we have established what a derivative is. All right. Now, with that said, all right. So let's do a practical example first. So if I have f of x is equal to x squared, I want to find f dash of x. So how do I do it? Well, f dash of x is limit as h tends to 0, f of x plus h minus f of x divided by h, right? This is what we have established. This is the definition of f dash of x. So we have limit as h tends to 0. Instead of x squared, I take x plus h squared minus x squared divided by h. And now if I solve this, I have x squared plus 2xh plus h squared minus x squared divided by h. So minus x squared plus x squared will cancel out, and I will get the expression 2x plus h, right? So if I divide by h, the two terms here, I get 2x as my first term and h as my second term. Now, if my h gets closer and closer and closer to 0, and if it's practically 0, then my answer is just 2x, right? So the derivative of x squared is 2x. Now, for every question, we won't use the definition. So we have this very important rule. It's the most important rule that we are going to use in this chapter, and it's that d of dx of x to the power n, where n is a real number. So it works for whether it's a fraction, whether it's a negative number, whether it's a positive number, it doesn't matter. N x to the power n minus 1. This is the most important rule that we are going to use, and we unfortunately will not prove this. Maybe we will. If I have time, I'll make a separate playlist for this. But this is the golden rule that we are going to be using for this chapter. All right. So now that we have discussed what the derivative is. We have looked at the definition using limits, and we know that the gradient, basically the derivative at a particular value of x, is basically the gradient of the tangent line at that x point. So let's look at some rules. Rules of differentiation. So we will now write, instead of writing it as, so this expression that I have written here, this is an operator. So this means, like plus, minus, multiply, this means take the derivative of x to the power n. So this is our function, or basically our y value, but this operator takes the derivative of the function. So I want to take the derivative, right? So d by dx, take the derivative of, so now if you come back over here, right, f of x, I gave you, using the definition, we figured out that the derivative is 2x. So if I tell you what is d by dx of x squared, this basically means what is the derivative of x squared? 2x. That is what you're going to give me. So d by dx of f of x, if I have two functions added together, then you're going to take the derivative individually. Plus d by dx of g of x. And secondly, if I have k, some constant times f of x, then you keep the constant and you just differentiate the function. So this basically qualifies the derivative operator to be a linear operator, but we won't discuss that. So these are two very, very important rules here. All right. The third rule, basically the exponent rule, is something I have already given, but let me write it again. D by dx of x to the power n is nx to the power n minus 1. N is a real number. All right. Sorry. So this is the most important rule that we are going to be using in this chapter for grade 11. For grade 12, we'll have more rules added on top. All right. So now, let's look at this rule. D by dx, we are going to cover this again in a future video, this one. If I have the product of two functions, f of x times g of x. So sometimes you will see this rule as d by dx of uv, where u and v are functions of x. And it's going to be u v dash plus v u dash. And basically that means that you keep your first function, you differentiate the second function, which is g of x, plus you keep your second function, you differentiate your first function. So now let's prove this, right? So if I ask you to find d by dx of f of x times g of x, then that is simply asking you to take the limit as h tends to 0. So let's f of x plus h, g of x plus h, minus f of x, g of x, divided by h. Right? That is what I'm asking you to do. Now, limit as h tends to 0. Now we need to add or subtract something. Let me think about it. If I add plus, sorry, if I add and subtract, right? G of x plus h, f of x minus g of x plus h, f of x, then that doesn't do it, because these two terms are the same thing. They're going to cancel out, right? F of x, g of x, divided by h. So my middle two terms are going to cancel out. So I have limit as h tends to 0. You don't need to know the proof. I'm just showing you if you're interested. So now, from this term and from this term, I can factor out gx plus h. And on the inside, I have f of x plus h minus f of x. And here, from these two terms, I can factor out f of x. And I have g of x plus h minus g of x. All right. Divided by h. So now, if you think about it, this is just limit as h tends to 0, g of x plus h times f of x plus h minus f of x divided by h plus f of x. So the limit you can just sort of distribute. So the limit operator works that if you have a limit of x tends to something, a, f of x, g of x, then you can do it individually. So that is limit x tends to a f of x times limit x tends to a g of x, provided they both exist. But using this rule, you are going to get the expression from this point. You're going to get limit as h tends to 0, g of x plus h, then you have f of x plus h minus f of x divided by h plus limit h tends to 0, f of x, g of x plus h minus g of x divided by h. So if you take the limit as h tends to 0 of the first part, you're going to g of x f dash of x. Because remember, this expression is just the derivative definition of the derivative. And if you take g of x plus h limit h tends to 0, that's just going to approach g of x. Plus from the second part, I'm going to get f of x g dash of x, because this part is a definition for the derivative. So that is how you get the product rule. And similarly, using the same idea, right? Using the same idea, you can get the quotient rule. But I'm not going to show the proof. But the idea is if you have f of x divided by g of x, you're going to get g of x squared. You keep g of x, f dash of x minus f of x, g dash of x. So that is the quotient rule. And these are formulas that you will need to remember. So this is called the product rule. This is called the quotient rule. And I will show you how to use these rules. And finally, we have something called the chain rule. It's basically related to the composition of functions. So basically, if you have this, then you are going to differentiate f with respect to g of x, and then you're going to differentiate your inner function. And that is the chain rule. All right. And if you're not comfortable writing this, you can also write it with d by dx notation. That is fine. But these are all the rules that you want to remember, and I won't prove the quotient rule. The proof is given in the textbook. But yeah, that is all that you need to know, and we can start solving some questions from the next video.